let's talk about stoichiometry some more. This is part 2 of my videos on stoichiometry. In this video, we will talk about converting from a mass of one thing to a mass of another using a balanced equation. And then also we'll include some liter questions in there if you are given liters of something, how to convert it to the mass of something else or to the liters of something else. All right, just as a reminder to you, stoichiometry is chemistry math. It's calculating relative quantities of reactants and products in a chemical reaction using a balanced chemical equation. So we just did in class, as well as in the video, mole-to-mole stoichiometry. So let's use this equation as an example. So in the last video, we talked about what these numbers that are in front of our chemical compounds actually represent. So those numbers actually are mole quantities. So if this is a recipe, then this recipe is written in terms of moles. So if we are asked to, for example, produce a certain number of moles of NO2, we can use, and we want to know how much, say, NH3 that would require to do that. We have a ratio, a 1-to-1 ratio of NO2 and NH3, so we should be able to use that ratio and the amount of moles of NO2 we're trying to produce to figure out how much NH3 we would need in moles, because this is written in mole quantities. The issue you're going to run into, especially in a lab situation, is that you rarely actually work in moles within a lab. You're given an equation written in terms of moles, but you'll be asked to either use a certain number of grams or produce a certain number of grams of something. And that's where it gets a little mathy and tricky, but you can do it because you already have the pieces. We just need to put it together. All right, so for example, I might ask a question like this. How many grams of NO2 could you produce from 15 grams of NH3 and excess oxygen? So let's kind of break this down and try to figure out what it's asking, what it's giving us, and also there's a couple of terms in here that might be a little confusing, so we should talk about those too. All right, so the first thing I want to identify is, what is this asking us to find? So what is it asking us to do? It's asking us to find grams of NO2. So we want a mass on NO2, and it is giving us the amount of NH3. So this is what we want, and this is what's given. It also has some weird term in it that might be confusing, where it says that you have excess O2. So I want you to notice that oxygen is one of your reactants in this situation. And this little term, excess O2, really just means that you have enough O2 so that all your 15 grams of NH3 will get used up. So you're not worried about your O2 running out. Now, sometimes it doesn't say this in the question, but sometimes it does, so I just wanted you to understand what excess O2 really means. It just means that your amount of NO2 isn't going to rely on your oxygen amount. Your oxygen, you have plenty. Your amount of NO2 is going to rely solely on how much NH3 you are given, which in this case is 15 grams. All right, so we know what we're starting with and we know what we're given. So let's just move some things out of the way here. We know that our equation is written in terms of moles, not in terms of grams. So we need to get this into the same unit that our equation is written into. So we're going to take our mass, or our grams of NH3, and we're going to do a quick conversion to get it into moles of NH3. And hopefully you remember that to make that conversion, you're going to need the molar mass of NH3. And then we're going to take that NH3 and we are going to convert it to moles of NO2. And we're going to do that using the mole ratio from the equation. And then once you're into moles of NO2, it's asking for grams of NO2. So you're going to want to then take that moles of NO2 and convert it to grams of NO2. And you'll do that using the molar mass of NO2. So we're going to make a number 1, 2, 3 calculations, or 3-part conversion. So you always start with what you were given, which is 15.0 grams of NH3. We got to get that into moles so that we can compare it to our equation, and we of course do that with the molar mass of NH3, which turns out to be 17.031 grams. So if we were to do that calculation, we would have gone this far. We would have converted it to the same unit that our equation's written in. We are then going to go mole to mole, so mole of NH3 to mole of NO2, using the mole ratio from the equation. So we know that from the equation, 4 moles of NH3 will produce 4 moles of NO2. So in this case, it just happens that it's a 1-to-1, 4-to-4, or a 1-to-1 ratio. And that'll cancel out moles of NH3, and at this point, we will have made it this far. We have gone to moles of NO2. Now we are going to take that number of moles of NO2 and we're going to convert it to grams using the molar mass of NO2, which is 46.005 grams of NO2 in a mole. Now, as I'm doing this, I want to point out how meticulous I'm being. It's a lot of writing, putting units on every number, but it really pays off in the end because you can see exactly what cancels and exactly what you're left with, so you can make sure that you are where you need to be. All right, I scooted that over a little so I have room for my answer. So if you were to calculate this, you would get 40.52 grams of NO2 produced. Now, before you just go and write down what your calculator gave you, I want you to think about whether or not this answer makes any sense given what you started with. So you started with a little less than a mole of NH3. How do I know that 15 grams is less than a mole of NH3? Because I know the molar mass of NH3 is 17-ish grams, which means 15 grams is less than 17, making it less than a mole. I also know that from my equation, it's a 1-to-1 ratio. So a mole of this would make a mole of NO2. And I know that a mole of NO2 weighs 46 grams. So it makes sense that because I have a less than a mole of NH3, that I would have less than a mole of NO2. So that should weigh less than 46 grams. I want you to start thinking about, does your answer make sense? Okay, let's do another example. So in this example, it says how many grams of water would be produced if 22.3 grams of O2 were used. So we know from the question that we were given 22.3 grams of O2, so that's what we were given, and that what it's asking us to find is grams of water. So this is what we want to ultimately end up with. So we're going from a mass of O2 to a mass of water. So our plan is to go from grams of oxygen given to moles of oxygen, because that's what our equation is written in terms of, and we'll use the molar mass of oxygen to do that. And then we're going to use the mole ratio between oxygen and water to get us to moles of water, and then we'll go from moles of water to grams of water using the molar mass of water. So let's set it all up. So our first step is to turn grams of oxygen into moles of oxygen using its molar mass. So of course grams of oxygen would cancel, and if we were to stop right now, we would be able to tell you how many moles of oxygen are in 22.3 grams. All right, we're going to then convert moles of oxygen to moles of water using our equation. So we know that 6 moles of water can be produced from 7 moles of O2. And we got that right from our equation right here. And moles of oxygen would cancel. And then if we were to stop right now, we would be left with moles of water, which is not what they asked for. They asked for grams of water, so we've got to use water's molar mass. So the molar mass of water is 18.015 grams for a mole or per mole. So moles of water would cancel, and we would be left with grams of water, which is what it asked us to find. And it turns out that it would be about 10.8 grams of water. So using 22.3 grams of oxygen in this recipe would result in about 10.8 grams of water. All right, and last we're going to talk about how to convert when you're given liters instead of grams, or if you're asked to find liters instead of grams from a balanced equation. So a couple things I need to remind you of. First of all, when I say liters, I mean only for gases. I'm not talking about liters of liquids or solids because their volumes aren't really affected by the environment, whereas gases are. So you will recall that a mole of any gas at standard temperature and pressure will occupy 22.4 liters. So from that, we can get this ratio, that 1 mole of any gas is 22.4 liters of space at standard temperature and pressure. All right, so for example, we have this equation for the production of NH3 from N2 and H2. And notice that it's balanced. So let's not forget that, first of all, if there is not a number in front or a coefficient in front, you assume that there's a 1 there. And then also that those quantities are moles, right? So this is 1 mole of N2, 3 moles of H2, and 2 moles of NH3. So our equation, again, is written in terms of mole quantities, not liters or grams. So this question, let's look at what it's asking us to find. So it's asking for the number of grams of H2, so that's what we want. You would need or would be required to produce 36.5 liters of NH3. So I want to point out it says liters, so this is what we want. So in this case, we are going to be given grams of H2, and because our equation's not written in grams, we're going to need to convert that using the molar mass of H2 into moles. And then we're going to take the moles of H2 and convert it into moles of NH3 using the mole ratio from the equation. And then once you've got moles of NH3, you're going to convert it into liters of NH3. And we're going to do that by using this relationship right here, that 1 mole of any gas will occupy 22.4 liters. So let's start with what we were given, because that's what you always start with. So we've got to convert that liters into moles, because we can't compare liters of NH3 to moles or of H2. We can only compare moles to moles using this equation. So we know that a mole of NH3, because it's a gas, will occupy 22.4 liters of space if you have a mole of it. So of course liters of NH3 would cancel, and at this point would be left with moles of NH3, which we can then use our mole ratio from our equation to convert into moles of H2. So we know that there are 3 moles of H2 required in this reaction for every 2 moles of NH3. So we got this ratio right from the balanced chemical equation. So then moles of NH3 would cancel, and if we were to stop right now, we would be left with moles of H2, which isn't what we want. We want grams of H2. So we're going to take one extra step, and we're going to use the molar mass of H2, which happens to be 2.016 grams. So moles of H2 cancel, and then it just becomes a matter of working out this math equation. and you get 4.93 grams of H2 that would be required to produce 36.5 liters of NH3. So now I could actually go into a lab and say produce 36.5 liters of NH3 using this reaction by measuring out 4.93 grams of H2 and a whole bunch of N2, right? We want excess N2 so we don't run out, and just reacting until this runs out, and I should be able to collect 36.5 liters of NH3. All right, let's quickly do one more. So in this case, I've given you a new reaction. This is methane. This is natural gas. Notice there's no coefficient, so we can assume there's a 1 there. And it's, of course, moles. So 1 mole of CH4 reacts with 2 moles of oxygen to produce a mole of carbon dioxide and 2 moles of water. And in this question, I want to know how many liters of CH4 I would need if I wanted to, or if I reacted it with 16.33 liters of oxygen. So how much of this would I need to completely react 16.33 liters of O2? So here's what we were given. So there's our given, and this is what we want. So we are going to go from liters of O2 to moles using this relationship that a mole is equal to 22.4 liters for a gas, and then moles of O2 to mole to CH4 using the mole ratio between those two in this equation, and then of course moles of CH4 to liters of CH4 using again the relationship that a mole of any gas is 22.4 liters. So why don't you pause and see if you can set this up and get an answer, and then unpause and see if you get the right answer. All right, so here I've set it up for you. So we're starting with our 16.3 liters of O2, and we're converting it to moles of O2 using this relationship that a mole of O2 is 22.4 liters. So you can see liters of O2 would cancel. Then we're going to take this moles of O2 and we're going to convert to moles of CH4 using the mole ratio that we got from the equation. And moles of O2 will cancel. And then we're going to convert moles of CH4 to liters of CH4, again, using the relationship that a mole of CH4 will occupy 22.4 liters because it is, of course, a gas, and you can use that relationship. So if you multiply across the top and divide by what's on the bottom, you should get 8.165 liters of CH4 that you would need to react with your 16.33 liters of O2.